Hi, this is Ms. Weiswald. We're talking about simple harmonic motion, and we're talking about this problem from Hecht, page 367, problem number 71. A small mass is vibrating in SHM. That's simple harmonic motion. Just jot that down up here to remind ourselves. It's moving in a straight line. In other words, it's moving back and forth in a line. Its acceleration is 0.40 meters per second squared. And we're asking, when you're at this point 20 centimeters from the zero, what is the period of oscillation? So we know that frequency is 1 over the period. And we know that frequency shows up in this equation for the displacement of a simple harmonic oscillator. There's an amplitude, and there's a cosine, 2 pi times the frequency times little t time, whereas this is big T period. And let's just make sure we've got these quantities here identified and label them real quick. We've been drawing this picture in class of a simple harmonic oscillator. You've got an amplitude and the period over 2, and then you've got a period here, and it repeats, comes back to the same point in one period, so about like that. And this is little t time, and this is x of t position from the equilibrium point. The equilibrium point is this line right here, of course, where x of t is 0. All right, so back to the question. Its acceleration is 0.4 meters per second squared, so I like that. Those units are good. And the point 20 centimeters from the zero. So we're saying there's some t, let's call it t1 maybe, where this thing is at 20 centimeters or 0.20 meters. So once again, that's just 20 centimeters. We know that we can get the equations for velocity and acceleration from the equation for displacement, taking the derivative. And so you get v of t, taking the derivative, equals minus a times, hang on, gotta do the chain rule here, 2 pi times f times the sine of 2 pi f of t. Cool thing about sinusoids, they just stay sinusoids no matter how many times you differentiate them. And this is going to be 2 pi f squared times a minus sign out front times a cosine 2 pi f of t. So once again, I took a derivative to get to here, and I took another derivative to get to here. So let's say you're not in calculus. We have talked about the slope of the curve being velocity. So imagine that this equation here gives you the slope of the, sorry about that, it gives you the slope of the x of t curve, and this gives you the slope of the velocity curve, which is acceleration. Okay, cool. So what you should notice, let me get a different color here real quick. This right here is basically x of t. So another way we could look at the acceleration with respect to time is minus 2 pi f squared times x of t, because that's what the a cosine 2 pi f of t is. So when x of t, let's say, equals 0.2 meters, let's just do this. Let's just say our acceleration, 0.40 meters per second squared, equals minus 2 pi f squared times x of t, which is 0.20 meters. All right, so once again, what I did is I took this relationship for a of t, which I'll give you on a quiz or something, and I said We know the acceleration. Let's say we're at some time. They don't tell us what time. Sometime t1. We said sometime t1 our displacement was 0.20 meters. That's right here. And then we said the question states that the acceleration is 0.40 meters per second squared. I think you can see then that we can solve this equation for f because we know what pi is. But in particular, let's rewrite this equation. So changing colors again here. Let's rewrite this equation in terms of t. So 0.40 meters per second squared equals minus 2 pi over t squared times 0.20 meters. All right, some of you might be saying there's a minus sign problem, and that's very good. What we are going to do basically is say, well, since it could be positive t or negative t, sorry, it could be positive displacement or negative displacement. Either way, about the origin, your accelerations are going to be they're going to be symmetrical about the displacement from the origin. If they're not symmetrical, you can just wait a little while and it will be symmetrical. In other words, here the acceleration is towards the equilibrium point, and here it's towards the equilibrium point, so positive or negative. Here it's positive or negative. All I'm trying to say is that we are going to kind of throw away this negative sign so that we can keep our square root legal, and we're going to solve this for t then. So what I get, let's pull a t squared out over here. So t squared equals 0.20 meters over 0.40 meters per second squared. So I put the t up, brought the 0.40 down, and I have a 2 pi squared times this whole thing here. And then t equals the square root of all of that, 0.20 meters all over 0.40 meters per second squared. But of course, I can just multiply by 2 pi because the square root takes away the 2. So we get, when I plug that into my calculator, 0.20 divided by 0.4, and take the square root of that, and then multiply by 2 and multiply by pi, I get 4.44. And units, what should the units be? So period is the time it takes, so seconds. Notice that the seconds came up in this fraction here, and then we took the square root of those. So t equals 4.44 seconds. Nice work. Now, let's go to the next problem. Next problem. This is in Hecht as well. This is actually going to be the quiz question. So let's take a look. A point on the very end of one half of a tuning fork vibrates approximately as if it were in simple harmonic motion, again, SHM, simple harmonic motion, with an amplitude of 0.50 millimeters. If the point returns to its equilibrium position with a speed of 1.57 meters per second, find the frequency of the vibration. Okay, so imagine you've got a tuning fork here. The ends of the tuning fork, let me change color, are vibrating back and forth. And if you look at them very closely. You can see them vibrating, or of course you can feel them with your fingers, but the point is it's a fairly small amplitude, so 0. So if the amplitude, again, is 0.50 millimeters, that means that that is 0.5, you've got to basically divide by 3, so times 10 to the minus 3 meters, which is what millimeters means, 0.5 times 10 to the minus 3. Okay, that's the amplitude. Remember, we can draw this curve here. You've got amplitude, amplitude, period over 2, period. This thing is going to, always write that right in the way. Let's get it out of the way this time. Anyway, here's minimum amplitude, maximum amplitude, and then returns to that point. So we do a nice little sinusoid through these points here. Boom. Okay. It returns to its equilibrium position. Once again, the equilibrium position where x is 0, that's where it crosses the axis. So let's highlight those right here. These are returning to equilibrium positions with a speed of 1.57. So v equals 1.57 meters per second. Notice that that is both a positive velocity, negative velocity, because you're coming from positive x of t and you're going towards positive amplitude, you're going to negative amplitude, right? And it's also a positive velocity, negative v, and a positive v as you're coming back from your negative displacement to your positive displacement, so positive v. We're going to pick which sign works for us in this equation, and we're looking for frequency f. For extra credit, I'm going to ask you also to compute the period, and I'm going to ask you to compute the acceleration at that point as well. Alright, so this is going to be xc. Alright. We write our equation for simple harmonic motion. X as a function of t is an amplitude times cosine of 2 pi times the frequency times time. We know that the velocity as a function of time is equals minus a 2 pi f times the cosine of 2 pi times f of t. Now here is the trick, and I'll do this let's do this in red again. When you're getting to your equilibrium position, what is the value for the cosine of 2 pi f of t? So the equilibrium position here is actually going to be where your displacement is 0. So if your displacement is 0, what is your acceleration going to be? I did this, I put this mistake in here. Let me fix this. This is not the cosine, it's the sine. Okay, so when the cosine is 0, it turns out the sine is 1. So this whole term here becomes 1. Because in equilibrium, let me just write this out. Because in equilibrium, the displacement equals 0. So this whole thing equals 0. That means this is 0. The only way 2 pi f of t could be 0 is if the cosine of 0, is if this argument here, this has to be 0. This has to be pi over 2. And if that whole thing is pi over 2, then the sign is 1. Okay, so the velocity now, we can plug it in. Here's what we've got. If that is 1, here's what our equation's turning out to be. Velocity at equilibrium velocity at the equilibrium position is minus a times 2 pi times the frequency times 1, because we said that was 1. So if I know that my velocity is 1.57 meters per second, and I know that my, we're going to absorb that minus sign again. I know that my amplitude is 0.5 times 10 to the minus 3 meters, and I know that that's 2 pi, and f, then I can solve for f, the frequency, which is in units of frequency is cycles per second. So the frequency is 1.57 meters per second divided by 2 pi times 0.5 times 10 to the minus 3. So that equals divided by 2 divided by pi divided by 0.5 e to the minus 3. I'm getting that the frequency is 499.746, or about 500 hertz, where hertz, of course, is cycles per second. So that makes some sense. Tuning forks are generally in audible frequency range, which is somewhere between like 100, maybe some people can hear lower, but 100 to maybe 750,000 hertz. Okay, so thank you for listening.